Okay, so in the last class, we have started at doing the continuous system. So first we have tried to see that how we can able to suppose if I just coming from the very beginning. So we first write the governing partial differential equation where we are considering that space and time variation both in that, and we have seen that how we can able to do the variable separation, so that there will be one function which will primarily describing the variation in the space, and there will be another function in multiplication which will be primarily denoting how the variation in the time is occurring. So by product of that two, we are trying to perceiving our solution, and then we are substituting that in the main governing differential equation back. And first we assuming that the time solutions are harmonic, and therefore we are trying to getting some solutions. And then we are assuming that okay, if it is harmonic, then we can able to see that first we try to calculate it what is the natural frequency of that. So in calculation of the natural frequency, we have seen we have to primarily find it out the mode steps and the natural frequency. So these two things we have to find it out for the free vibration problem. And once we are solving for the forced vibration problem, then force is known, therefore we can get a definite values of the shape. All the shapes we are getting definite values, and then we are adding them, and we will get the solution. So that we have seen. And after that we were discussing, we introduces the state vector, that what is the state vector, and from state vector how we can able to solve the natural frequencies of a particular system, of a particular beam or some system. And that is important because what happen in case of bar, like okay, we are having like a 2x2 matrix that can be easily solved. But once we are talking about the beam or some beam, it is 4x4. Now if we are going further complicated structure, then it will become very difficult to perceive that how we are going to solve it. So that is one problem. And then we have seen that how we can able to make the transfer function transfer matrix approach, and how to make one submatrix of the transfer matrix to 0, and then means to singular, and from that singularity we will establish how the variations are coming into picture, so we can able to calculate what is the natural frequencies. So that way we can able to calculate that. Then we started introducing that by altering the position of the state vectors, how we can able to get the spectral element matrix. And we have also introduced that what is the difference between the spectral element and finite element formulation. In finite element, spectral element is also look very similar to the finite element, because in the finite element also in the left hand side we are having the force, and then right hand side we are having the displacement, whereas in the transfer function we are having the state of left hand side and versus right hand side. So that is the correlation between the states. And but here once we are expressing it into the spectral element matrix, then it is actually correlation between the forces with the displacement vectors. So that is the correlation between these two vectors. And we have also discussed that by altering the relative positions in that matrices, we can able to get that get from spectral to transfer and transfer to spectral, that we can able to do. And then next case is that if we do not need the transfer function matrix, rather we try to just formulate what is the spectral element matrix, then also we can able to go from the very basis of the shape functions, as we have done for the finite element cases. So in finite, so there if you see, like we actually express that way that yeah, so this is our main equation was, so like once we are getting that lambda value, we substituted it, so there are the four solution of lambda is coming for beam. And now once we are doing it for bar, maybe there will be two solutions. So that depends on what is the order in the spatial domain. So based on that, how many coefficients will come, so that we will decide it. So then phi, which is the displacement we have written like, and then theta we have written it like this way. And if you see, our displacement vector can be written like this way, that unknown, and d vector can be represented at k into x with the v. Now if you do, so v equal to k inverse of d. Okay, so we get the v. Now if you try to express the phi x, so phi x, it will be e to the power of lambda x into e to the power of lambda 2x, e to the power of lambda 3x, e to the power of lambda 4x into b. Now instead of b, if you substitute that k inverse of d, you can get this portion n into k inverse. That will gives you the shape functions. Now once you get the shape function of a particular element, then it's a exactly similar process as like the finite element we can do. Okay, so for example, now maybe, so do you want me to repeat this portion a little bit and then start, or it is okay if I just go ahead from here? Repeat. Okay, no issue. Let me repeat it. No problem. No problem. So suppose if you see that was my beam. So in that thing, this is my W1, theta 1, W2, theta 2. If I see the forces, V1, M1, V2, M2. We have discussed in the last class that this representation is for the spectral element representation. If you remember, in the finite element, once we are representing anything, we have to have the forces and the displacement in the same direction. We cannot have them in the different direction. That's not possible. Okay, so this way we have to express. But if you see in the general transfer, so that is for the ACM, spectral element. Now if you see for the transfer, what we assumed, that is my V1 left up and M1, V2, M2. So you see here this M2 and M2 is same, and V1 and V1 is same, but these M1 and these M1 are not same, they are opposite. So once we are having it in transfer, that definition of M1 in the left hand side and V2 means the shear force at the right hand side need to be altered. Don't forget that. If you forget that, your sign and all those things will be crazy. Okay, you will not get the solution properly. Okay, so this thing we have to change. So once you are converting from transfer to spectral, you have to alter that sign also. Don't forget that. Okay, so now if you see in case of the transfer, how we wrote. So in transfer, we wrote it like this way, that the state vector of left hand side or maybe right hand side, that is W1, theta 1, V1, M1, or maybe I'm just putting it like this way, equal to the transfer matrix times W2, theta 2, V2, M2. Okay, that is my transfer matrix way. Okay, it can be opposite also. Means theta means you can put theta 2 here and theta 1 means, so that is theta 1, that is theta 2. So you can also vice versa. Okay, so capital theta can be in the left hand side. So that way, accordingly the T will be calculated. Okay. So that is the in case of the transfer. That is the transfer matrix. But if we see in spectral, what will happen? Now in case of the spectral, what we are doing? We are doing it V1, M1, V1, M1, V2, M2. That will be with S matrix, spectral stiffness matrix, with W1, theta 1, W2, theta 2. Okay, so that is happening in case of the spectral. So now the point is that how we can able to define that. So previously we have seen how we can define this one. Now if I try to see how we are defining here, so W x comma t, we have seen that will be nothing but phi of x into q of t. We can Forget the q of t, because q of t will be automatically sorry, you say this one, inspector. So that's why I put, like, here I put a dash, so that dash will representing the transfer and without dash is representing the spectral, so that we don't need to be worried. Or if you do not want to put it differently, actually they're not different, then you can actually change the sign also. What we did in the last class, usually we change the sign, that is also fine. Okay, but once you are doing it in the spectral completely, then we generally do not change the sign. We generally put the proper sign, just like we assume it that this is like this way, and then we do it. Okay, I think this is the better way to do, putting the dash, so that dash representing the transfer and normal one representing this. Okay, so we have this way. Then phi x can be, so like once we are substituting that into the main equation, so main equation was ei into del 4 phi, sorry, del 4 w del x4 plus rho a into del 2 w del t2, that will be equal to 0. Okay, so now once I am substituting it here, I will get it like ei into phi 4x plus minus rho square omega e into phi x, that is equal to 0. So from this equation I can write phi x will be equal to v1 into e to the power lambda 1x plus v2 into e to the power of lambda 2x plus v3 e to the power of lambda 3x plus v4 e to the power of lambda 4x. I can able to say that. Agreed? Because it's a fourth order differential equation, so obviously this is the root of that. Okay, we get that. Now, so this one is coming. Now if I see that if I try to imposing the boundary conditions, that is and also like w of 0, that will be nothing but your w1, that will be equal to phi of 0. So that means you are getting v1 e to the power of lambda 1 0 plus v2 e to the power of lambda 2 0 plus v3 e to the power of lambda 3 0 plus v4 e to the power of lambda 4 0. Okay, and that is phi, and then theta x, which is the rotation. So theta x also you can get it v1 lambda 1 into e to the power of lambda 1 x plus lambda 2 v2 e to the power of lambda 2 x, like this way. Okay, so then theta 0 should be equal to theta 1, that will be equal to phi dash 0. So that will be lambda 1 into v1 e to the power of lambda 1 0 plus lambda 2 v2 e to the power of lambda 2 0, like this way it will come. Okay, so now if you see that I have to express w1 theta 1 w2 theta 2, what will I do? I will do it like e to the power of lambda 1 0, e to the power of lambda 2 0, e to the power of lambda 3 0, e to the power of lambda 4 0, then lambda 1 e to the power of lambda 1 0, lambda 2 e to the power of lambda 2 0, lambda 3 e to the power of lambda 3 0, like this way. Just one term I can also write it. And then here it will be e to the power of lambda 1 L, e to the power of lambda 2 L, like this way this terms will coming. Just same repetition with v1, v2, v3, v4. So this is my b vector, this is my d vector, and this is some my maybe my I can just call it k matrix. So this k matrix, please pay attention, this k matrix is a definite term, means a definite matrix. All the terms are defined, because if you see e to the power lambda 1 0, that will be nothing but 1. Okay, because it will be e to the power 0. Then similarly lambda 1 into e to the power of lambda e to the power of lambda 1 into 0, so that will be again lambda 1 only. Then next term will be e to the power of lambda 1 L, that is also a definite value. Okay, so this matrix is known if lambda is known, or we can say this is dependent on lambda. Simple. Either we can say this is dependent on lambda, or lambda is also dependent on omega, because if you see here, once we are solving, so lambda is also dependent on omega, so we can say k is dependent on lambda or omega. Okay, now if we see, then how we can write b equal to k inverse of d. And now if I try to write the step function, I can write it phi x equal to e to the power of lambda 1 x, e to the power of lambda 2 x, e to the power of lambda 3 x, e to the power of lambda 4 x, that in multiplied by k inverse into d. Okay, so this k inverse is a 4 cross 4 matrix, d is 4 cross 1 matrix, b is 4 cross 1 matrix, and this is 1 cross 4 matrix. So if I just do it, you will get something, a term which will be 1 cross 4, and this each term is basically your shape function. Agreed, all of you? You can try to, once you are reading that, please make a comparison with the finite element, how you are deriving the shape functions in the finite element. Do a comparison, you will very clearly understood that. Okay, if you want to also see, there we are assuming some variation. So like we wrote, like for example, if we are taking a bar, what we do, we have this one u1, this is u2, we assume like a linear variation. So at x distance, what will be my value? Ux will be u1 plus u2 minus u1 divided by 2, sorry, u1 minus u2 divided by L into x. That is my function for a particular point. Now you wrote that wrote this way so that we can try to capture it in the terms of u1 and u2. So if you see, that will be with u1 1 minus x by L into u1 plus x by L into u2. So you say that u of x equal to 1 minus x by L and x by L with u1 and u2, because u1 and u2 are the two degree of freedoms, and we try to write the domain or the variation of the function, or maybe the field variable, the variation of the field variable in the terms of the degree of freedom. So if I see it in terms of the degree of freedom, then this is coming. So we call that 1 minus x by L and x by L are the two shape functions. Agreed? So this way we will get here also the shape functions. But you can understand now this shape function is dependent on what? These shape functions are dependent on the frequency, because your k is dependent on frequency, and you are getting it as the k inverse of omega and multiplied with that predefined function that we are multiplying, and we are getting each term. So here the shape function becomes frequency dependent. That is like a very, very vital point, and that is one of the prime difference between the spectral element matrix and finite element matrix. So here, what is the advantage? Then we will go to the disadvantage also. It's just the exact step, because we are solving the differential equation exactly. We are not assuming the field. If you see here in the finite element, we are assuming the field. That field is varying linearly. But here we are not assuming. We are solving the differential equation, whatever it is coming. So we solve that and we are getting it. So that is not an approximation. So spectral element is not that approximation. Yeah, now if you say that solution itself is the approximation, then I cannot say. But whatever is the exact solution of the differential equation, that tells that yes, this is the exact shape function for that. Okay, now if you see the next case, we are getting this way. Then additionally, so this gives the exact position. Second point, very interestingly, it is frequency dependent. Now, for example, you are trying to studying something in the very high frequency. Some study maybe you are performing which is very high frequency. So in that case, what will happen if you do it in the finite element? Your mass. So generally, like once you are having a very high frequency, then excitations once you are plotting, they have like some sort of like a wavelength type thing. So that wavelength also become very high frequency, wavelength become very small. And now once that, like suppose there is some blast or something happened, very high frequency event happened. So this thing is get like your medium is getting some sort of reflected shape, and that is, if it is very high frequency, then you will see that this variation will be in the very close, very fine portion, very small portion. It is confined it. Now, for example, now you have in finite element, you have to refine your mesh to capture that thing, because if your like for example your vibrator structure is like that, and you cannot take a mesh size like this way, that's impossible, because you already assuming that your variation is linear. So this single element can give only this type of result, that cannot give this internal fluctuation, because there is no inbuilt thing inside to capture that. But the benefit of this is here that with the frequencies, increasing frequency, its lambda will get adjusted automatically, because lambda is the function of frequency here. So automatically this shape will automatically come, and you do not need to bother with the meshes. And this is almost like a mesh-free method, that you don't need mesh. It is just a single element, you just model it as a single element. Done. But obviously, if this is so good, then finite element would not even grow. But if you see, finite element is the most dominating thing. Spectral element maybe very rare people know that whether that really does it exist or not. So obviously that finite element has its big advantage. So the advantage of finite element is the generalization. It is general, it can be applied for almost anything. Now here, if you know the differential equation or solution of the differential equation exactly, you can able to solve the spectral element. But if you don't know that, if you cannot able to form that governing partial differential equation, you cannot able to solve the difference, cannot able to formulate the spectral element method at all. It's not possible to formulate it, because you don't know it from where to formulate it. Like for example, if I give you a problem that a beam having some cutout in between, it is extremely difficult to formulate in the spectral. Means suppose, for example, if I just draw it, like suppose for example we have a beam and we have a cutout like this, something like castellated beams or something. How will you do? I can try some typical spectral element to do that, but suppose for example if I going to do it, I will discretize here, I will discretize here, I will discretize here, and this. So I will discretize the full thing in the 4 part, and then I will do it. That will give very good result, no doubt on that. But now if you see, modeling this part will become a tapered, like you have a one portion is more, another portion is less. So what will happen, your ei del 4u del x4 plus rho a del 2u or del w del t, that is not valid, because now your I is function of x and a is also function of x. So once they are become function of x, you cannot directly write that way. So there actually some Bessel function and all those things starts coming into picture. Means your approximation of the phi x, which was very simply like we can just writing b1 lambda 1x, b2 lambda 2x, that will be no longer valid. Then these basis functions R will become something like we are using Bessel function or some Henkel function. So these are like a quite complicated things we are using, and therefore that is not that easy stuff to solve. Like for example, you are try to doing a finite element and you are thinking yourself that okay, what should be the shape function of that? Can you really able to deliver any project? Think it from the practical point of view. That's not possible. That's not possible. So that's why that element and all those things are predefined. And obviously, for doing the spectral and all those things, user has to be also in that level. Means you have to really do these things. You have to understand really what is the shape function and all those things. But if you see the finite element, we are using means even our like those who are just joined or maybe sometime with some basic training also. Maybe non-engineers are also using the STAAD and some other softwares. Maybe most of the companies people are also doing that. So that is not possible. If you people are writing the code with the spectral element, it's impossible. It's impossible. Truly, that you have to then identifying first that okay, what should be the function for that. That's not possible. The way to do it. So that's why the finite element is very general, used that much, but spectral has this limitation with that. But if you can do it with the spectral, you will get the exact solution. That's also true. Oh, and then another problem is also there with the spectral. If you do with the finite element, you will end up with a matrix which you can directly able to solve. Like for example, if you see, like for I just give you a quick example on that. So here, once we are making that full stiffness matrix, it will come. If you see that will come from basically omega, and that will be some transcendental function of omega, because our transfer function, if we are just shifting row and column, it will give the spectral element matrix. And transfer matrix, if you see, that is have each element is like sine omega t plus into cos omega t, maybe plus cos hyperbolic omega t. Like this way these functions are actually. So these are very transcendental equations. They are not directly, you cannot get a solution. Like suppose if I give you a example that okay, just do it like this way, that cos of lambda into cos hyperbolic lambda plus sine lambda into sine hyperbolic lambda equal to u. Tell me what is the solution of lambda? That's not easy thing. That's not easy thing to do. And once you do with the spectral, once you are equating it to 0, that means what happened? You have a matrix and you calculate its determinant and you are writing it equal to 0. So what will happen? That all the transcendental equations, they are in the element form. Now they are clubbing together, make a big expression. And this is a small version of that. You will get some quite long equation with this type of form. Now the question comes, how will you solve it? You make that, very good. After that solution, that itself becoming a big problem. So any idea, by the way, how we can able to solve this type of equation? Suppose if it came, how can we solve this? Obviously, you cannot find any general solution directly. Maybe some cases you could, like if it is like cos lambda L, you can get the solution. But if this is something like that, not possible. So in those cases, what we generally do, we take the lambda and we plot the function fx, and we try to see where it is cutting the 0. And so if we plot it like this way, so that will come like this. We can say, okay, this is my solution, this is my solution, this is my solution. So you have to use some sort of like bisection method or root finding method or maybe Newton-Raphson type thing to find out what are the solutions. So you can now able to realize that where are the complexities with this type of exact method, and there the accuracy will be again reduced, because once you are using this type of method, again the accuracy will be reduced. So these are some of the flaws where actually the things get stuck. Okay, like we have done several work on this type of things, that how we can able to improve this calculation and all those things, but yeah, these are like complete research things. You cannot even do that in the class. It's not possible. Yes, so we can get this type of solution. So, and that we have to try to solve it. Okay. So these are some of the fundamental problems for which spectral element not that popularized compared to the finite element. Because finite element does not have this type of problem. In finite element, how we will get omega square m plus k, that will be equal to u. Simple. Once you are solving the eigenvalue, you will get it in this form. M is a matrix, k is a matrix, so you can directly solve it using the eigenvalues, and you will directly get that because their omega, m and k are not dependent on frequency. These omega and k, these m and k are definite values because you know the shape, function, and all those things. They are not frequency dependent, so you will get m, the values, k with the values. Directly do it, and you get solve the eigenvalue. You will get that. But here, what happened? Instead of having like this way, you are having some expression where omega is function of function, something like that, and that is getting equal to 0. Oh, that solving this is quite difficult. And it needs like a serious level of effort to solve that. And also, suppose if you think like you are making a program, if you put this way, you can check it, you can get. But otherwise, you need a proper method or algorithm to find that. And often, some of the cases, it is also possible that two roots are coming very close. That also happens because this is I just typically draw. It may happen like this way that it will go cut. It could happen. It's a function. It can go like this type of ways. Now, if it is very close, so then it will again depend on the discretization of the lambda, that how well you are discretizing it. It may skip some values. So these are very problematic. These are very problematic. Like for example, if this type of scenario, if you do the Newton-Raphson, if you just pick a point, then maybe it will identify here. If you pick a point, you will identify here. But this point you cannot able to identify. So these are the challenges with that. So closely spaced roots and all those things, identifying is a big challenge. Big challenge. Okay, so this thing, if you try to search anytime, this is known as the nonlinear eigenvalue solvers. These are not linear eigenvalue solver. Linear eigenvalue solver is this is the linear eigenvalue solver, and these are the nonlinear eigenvalue solvers. We are doing like a several extensive work on that nonlinear eigenvalue solvers, but yeah, that's like a full research level thing, that how we do that and all those things. So there are several algorithms we have to use, and that is almost like mathematics. Then you will feel like, okay, I don't know why you are doing it in engineering. That is mostly like mathematics things. Okay, no issue. Yes, so yeah, so this thing is done. So now maybe can we do a small problem and try to see how we can able to do all those stuffs. So let's take like we have a beam and put a mass, tip mass on that end. Previously, once we are solving all the cases, we just have like a normal cantilever. Now just think we have a cantilever beam and with a tip mass. So M mass is added here. So this is E I rho A, and we have a mass. How can we able to get that? What will be the solution? So let's do it in the normal way. I am not using any matrices or all those things, because matrices, if I going to use, I'm not able to solve it exactly, because that matrix like 4x4 matrix inverse and all those things will be problematic. So suppose if we try to see how we can able to do that. What are the steps? So yes, please, equation of motion. So equation of motion. So how, what should be the equation of motion, please? Like let's say it's all abundantly simple. So EI del 4U del W del x4 plus rho E into del 2W del T2, that will be equal to 0. Okay. Will that be 0? Mass. Now if you see, there could be several ways of doing it. Now, if you see that mass is only at the right hand side, so how can we able to incorporate it into the domain equation? That is a different thing. That is the not domain equation. That is the boundary conditions. Okay. So if we are going with Mr. Ghulam's idea, then we are not implementing it in the difference domain equation. Domain equation I will leave it as it is, and we will just implement it in the boundary conditions. That is okay. So that is my domain equation and my boundary conditions, BC. So in BC, what will be the other terms? So if you see W of 0 should be equal to 0, I just think 0 and this is L. W of 0 equal to 0, theta of 0 equal to 0. Then how? Yes, please, please, please. You are very close. Yes, 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 yes. Perfect. Yes, your shear force at L. Think it very carefully. Okay, before we go for shear force, we know bending moment will be 0. So simple thing first, make bending moment 0. Now the shear force term. Yes, so shear force term, if you try to see what is happening. Let's see. So we have in the beam, we are assuming that this is going downward, that is the positive. Like once we are solving the normal way, you just follow that. Only accept the spectral element if you are trying to formulating, then change that sign. Okay. Otherwise, just follow whatever the sign convention you are following, because your domain equation is compatible with the signs. Means if you change here like a left up, right down, instead of doing that, if you do it something different, your domain equation can change. So that you have to be very careful with that. Okay. So here, like if you see, this is my V L. Okay, going down. Okay. Now we have that mass. Now mass, if we have that mass, will have inertia force. Exactly. We are not applying any forces, so we just only have the inertia force. Now if you see, in that point, where is the displacement? Displacement is going upward. Okay. If the displacement is going up, which side the inertia force should be? Downward. So your inertia force will be m into W double dot. Perfect. Any doubt? W double dot L. Exactly. W double dot L. Because W is generally the full. So that is actually W of x, because it's a continuous function. So we have to define that that is at the L point. Okay. Makes sense? Now, but that also not serves the full purpose, because this is VL. So if I think that is a cut, because always once we are doing the shear force or bending moment, we can get it from the cut. If we not cut, we will not get bending moment, we will not get shear force, because they are the internal reactions. Okay, so we have to cut it there. So once we cut it there, this will go here, this will go up, VL. Now we can balance that. Agreed? So if we balance this one here, so you can say VL will be equal to M W double dot. Agreed, all of you? All of you agreed with me? So this is now my boundary condition. So I can say M W double dot A. Okay, please. Sorry? Strain will be 0. Here how will you define the strain, because this is not a bar problem. in bar problem we can easily define the strain, that is like a force divided by area will gives you the stress divided by the Young modulus will gives you the strain. But here defining the strain is big problem because you will have the bending as well as the shear, both the strains are there na. So that's why that is why actually if you see we exactly moment is 0, so there is a bending strain will be means bending strain will when the curvature will become 0 actually, but you will have then the third derivative, this will be quite important. Okay, I mean what the way I generally try to do it, I generally try like if you are having an axial type thing, then we can go, means it is better to do the force balancing, because force balancing we all know how to do it, like we have the bending moment diagram and shear force diagram, if you see how we plotting, we just do like that way. So you will get whatever the force term is coming there, and you already express the force term, whatever the strain and all those things are there na, you already express that, because once if you see the bending case, that is not that easily to write the strain. In case of bar we can easily write it, but in the beam it is difficult, and if we are going further, writing it in terms of strain will be very difficult, because only strains. So because those derived parameters actually if you see they are the combination of the strains. Like for example if you take the Timoshenko beam, there will be a bending strain and there will be some shear strain also. So both the components comes into picture together. So but you defined your rotation total and then the bending moment. So why not just use the bending moment expression, whatever is coming there. Okay, so that way it will be much easier. Okay, and maybe in the next class I will try to show also some portion of the Timoshenko beam. Then I think that will be much more clear that how we can able to incorporate that thing, the different strains, how they are actually coming and making those parameters. Okay, so we'll have like this. Okay, now here again the question comes, how will you solve it? So we have these boundary conditions, agreed? So first point here we can able to write W of x comma t, that will be equal to phi of x and q of t. So what is our objective to calculate here? Free or force? It's a free vibration problem, because we try to calculate for the natural frequency. That okay, we have a beam and we put a tip mass on top of it. So try to calculate the natural frequency. Okay, so how will you do it? We'll add phi x and qt. What the things are there. Now if you substitute back here, ei phi for derivative x plus rho e omega j square phi j. Actually j I am putting because there is actually in summation from, we have discussed that we can write it in the summation from, then that will be equal to 0. So each term we can assume that they are 0. That is 0. Okay, so now what will be my j? This is equal to a1 into the power lambda 1 x. So that is j. Or maybe I just put it k. K equal to 1 to 4. Okay. So once I put that, and what will be my lambda? So lambda solution will be lambda 4 into ei equal to rho e into omega j square. So lambda j4 should be equal to rho e divided by ei into omega j square. Okay, so we get that way. What are the lambdas we can get in terms of omega? And now my target is to calculate. What is my target to calculate? This AK, or maybe I'll just put it BK. BK will be better because E and A will be confusing. So my target is to calculate the B and calculate the omega G. Okay. So if I just first substitute that full thing here in the first equation, what can I get? I will get b1 e to the power of lambda 1 0 plus b2 e to the power of lambda 2 0 plus b3 e to the power of lambda 3 0 plus b4 e to the power of lambda 4 0, that will be equal to 0. That is my first equation of motion. First boundary condition I just implemented. Okay. Second boundary condition. Second boundary condition will be V1. So if I see the first equation, I can rewrite it V1 plus V2 plus V3 plus V4, that all equal to 0. That is from my VC1. So once I implemented the first boundary condition, I will get that. Agreed? Then second boundary condition. Second boundary condition, if you see, V1 lambda 1, V2 lambda 2, V3 lambda 3 plus V4 lambda 4, that will be equal to 0. That will be my VC2. Okay? Agreed? All of you? Then third equation. Third equation is how much? That will be the second derivative. So we will have lambda square V1 e to the power lambda 1 L plus lambda 2 square V2 e to the power lambda 2 L plus lambda 3 square V3 e to the power lambda 3 L plus lambda 4 square V4 e to the power lambda 4 L, that will be equal to 0. That is from my VC3. Okay. So here, so you can see that we are having three equations here. Okay. What are the unknowns? Just quickly. Lambda is unknown. Okay. And V1, V2, V3, V4. So we have 5 unknown. 5 unknown? 8. No. Yes, that's a good point. Actually, you can say 8 unknown. But if you see lambda 1, lambda 2, lambda 3, lambda 4, they all are dependent only on omega g. So therefore, you can say that they are actually, this will be lambda k. Yeah. So this will be lambda k. Yes. So they should be equal to the lambda means the omega g. So that omega g is a particular value. So there is a 4 value of lambda k for a particular value of omega g. Okay. So we are having basically 5 unknowns. They are V1, V2, V3, V4 and omega g. Agreed? So we have 3 equations this way, and last equation is the VC4. So VC4, if I see, VC4 is coming V. Yeah, here now we can see that here actually you have to multiply with the EI, because M is nothing but EI into this. So to multiply with the EI, but EI multiplying or not multiplying will be equal to 0, so it doesn't matter. But here it will matter, because it is not equal to 0. So please keep that thing in mind. Don't forget, if there is something equal to, then please consider that force and moment has the EI term. Don't forget that. So if I just put it like this way, okay, that will be M into how? You have, so M omega square. Omega again will come in here as well. They are calculating the natural frequency, again the natural frequency comes here. So life is getting full complicated. Life is getting so that into your full 5. So that will be again V1 e to the power lambda 1L plus V2 e to the power of lambda 2L plus V3 e to the power of lambda 3L plus V4 e to the power of lambda 4L. That's whole thing. So M into omega square with a minus sign will be there, omega j, V1 e to the power of lambda 1L plus V2 e to the power of lambda 2L plus V3 e to the power of lambda 3L plus V4 e to the power of lambda 4L. That's something quite long. So that way we can go, or else we can make it in the matrix form as well. Okay, so if you see here, we can do the matrix way also, that we can write first, that is like your W theta in P, sorry, B1, B2, B3, B4, and I am just making it this way, B1, B2, B3, B4. Yes, so we can make it like this way, simple, so that we can put it 1, 1, 1, 1. Our first equation done. Second equation will be lambda 1, lambda 2, lambda 3, lambda 4. First equation done. Third equation will be EI is multiplied here with, oh no, EI is not required, EI is gone. So lambda 1 square e to the power lambda 1L, lambda 2 square e to the power of lambda 2L, like this way. And the next one, that is interesting. Here if you try to see how it is coming, EI into lambda 1 cube into e to the power of lambda 1L plus m omega j square e to the power of lambda 1L 4 into B1. Similarly, plus lambda 2 cube e to L plus m omega j square e to the power of lambda 2L into B2. Huh? Perfect. EI fully multiplied here. Yes. So like this way, we can able to get each term. So that terms we can put it here, 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 here. Okay. Make sense? And that is equal to 0. So obviously your B1, B2, B3, B4 cannot be 0. Then it will become a trivial solution. So whatever you are getting here, that should be equal to 0. So if that is should be equal to 0, then we can get, so you can again make a determinant, and that determinant will be equal to 0. So it will again lead to some transcendental functions. That transcendental function will be 0. So solving that, now if you see, this function will be only dependent on omega g. All the terms are dependent only on omega g. There will be no B1, B2, B3, B4. So everything is known. You just have a single term you have to find it out, that is omega g. And it's a transcendental equation, so it will keep giving the solutions. As many as you are doing, it will give the solutions. Okay, that thing is done. We can identify how we can calculate the omega g. Okay, now once we have calculated the omega g, now the way we have calculated the omega g, now what happened? You have this full matrix, you plug the omega g into it. You have the full expressions, now you put the omega g value. Okay, so your this matrix will become so once you put the one value of the omega g from the solution, this matrix again will become 0. Makes sense? But what is our objective? Here we already get the omega g. Now we are looking for P1, B2, B3, B4. So how we can do that? We can assume someone to be 1. Like let's say assume B1 equal to 1. And we have this full thing 0. Okay. So what we can do, we can reduce this matrix, like we have a populated matrix here, full thing written. So we can try to reduce this matrix to a lower triangular matrix. and that can give the quick solution for that. Or else we have like full equation here. Like for example, if I just taking the first equation, b1 plus b2 plus b3 plus b4, that will be equal to 1. That will be equal to 0. Now you think your b4 is 1. So you will have b1 plus b2 plus b3 plus 1, that will be equal to 0. So like this way, then what will happen? Your solution will be reducing to 3 cross 3, not 4 cross 3, and then you can able to get the solution. Means, or if I try to just show it, so this matrix, if I see, is like this way. So I just cut it. So they are like a 3 cross 3 matrix. This is 3 cross 1 matrix. This is 1 cross 3 matrix. This is 1 cross 1. So what can I say? So this is maybe, I say S11, S12, S21, S22. So you can say S11 into this, maybe B1 and this is B2, or maybe D1 and D2. So this D1 plus S12 into D2, that will be equal to 0. So that will be 3 cross 1. Okay. Okay. Now you see D2. What is your D2? D2 is nothing but your 1. So can I say S11 into D1 should be equal to minus S12. Can I say that? If this is the case, then D1 equal to S11 inverse S12. And we are done. And what is your D1? D1 equal to V1, V2, V3. And this is, yeah, and your D2 is nothing but D1, D4 only. So you are just basically assuming D4 and you are getting the solution. So this is also another way how you can able to do that. You have write all the equations there, take the first portion, take the first submatrix and invert it and multiply that and you will get it. And you have already substituted for the omega. So now that, like for example, if you see here, so your first one will be, if you see 1, 1, 1, then lambda 1, lambda 2, lambda 3, then I think what was there? Lambda 1 square e to the power lambda n. Lambda 1 e to the power lambda 1l, lambda 2 e to the power lambda 2l, lambda 3 e to the power lambda 3l. That into this matrix should be equal to that vector. So vector will be coming from here. So what? That is 1 lambda 4, yeah, that one. That will be 1 lambda 4 and lambda 4 e to the power of lambda 4l. That will come. So you just take an inverse and multiply with it with a negative sign. So that will gives you V1, V2, V3. And you can see as these row are not same, because lambda 1, lambda 2, lambda 3, lambda 4 are not same. They are the different, because one is plus, another is minus, another is with I, another is with minus I. So they are different. So they will not cancel out with each other. So that matrix, this small matrix is not singular. This is not singular. This is not 0. This is not 0. So you can able to do the inversion of that. And that will gives you the solution. So is that clear? Although obviously you have to do it. Like, yeah. Please. Last row. Which one? This one. You can see that here in this equation you are taking all the terms you put. So what happened, now you are taking them all in the left hand side and start clubbing them together. So you will have like coefficient v1, v2, v3, v4, and there is no constant term left. So all the terms are coming like a coefficient of v1, coefficient of v2, coefficient of v3, coefficient of v4. So they will be equal to 0. Got that? Best thing is try once. Try once, I think you will get that whole thing. Because this type of thing you have to do, have to practice, no option. So yes, please. One minute, please. Yeah. Sorry, omega
and omega and double and omega 5.
Sorry, I didn't get. Please, just a minute. You want to say this line?
Yes.
Yes, okay. Just do the balancing of the force.
No. Below that, now equity.
This one?
Yes.
Okay, let me do it. Okay. My WL is phi L, that will be V1 e to the power of lambda 1L plus B2 e to the power of lambda 2L plus B3 e to the power of lambda 3L plus B4 e to the power of lambda 4L. Okay. Now, double dash L will be omega minus omega square into phi L. So that will be nothing but just you are multiplying with means m omega square obviously. So that will be that, and so you can just understand that will be multiplied with the m omega square. So now once you are putting it, so your left hand side is coming like Vi into lambda 1 cube e to the power of lambda 1L plus lambda 2 cube e to the power of lambda 2L, like this way, equal to minus m omega square v1 e to the power of lambda 1L plus, agreed? I'm not writing all the terms down. Okay. So what happened? You are now clubbing them. Okay, here we will have a v1 also. v1, v2 like this. So now if you see the terms of v1s, so they are ei lambda 1 cube plus m omega square e to the power of lambda 1L into v1. Same way v2, v3, v4. v2, v3, v4, that will be considered. So that's why that is become 0 also, and all the terms are getting clubbed with v, and we will get that. Huh? How solve it by hand in exam? Yes, that's a very good point. Yes, obviously. Now I can tell you the trick. You can do one thing. Instead of writing that in e to the power term, you can also write it in terms of cos and sine. Okay. Nah, there you will get some sort of reduction. Why? Because if you see, no, why hyper term will be there? Yes, exactly, hyper term will be there. But what will happen? You are substituting the values. So in the first equation, once you will substitute, so your first equation will become like v1 into sine of lambda. Just let me see. Very good. So like v1 into cos lambda x plus v2 into sine lambda x plus v3 into cos hyperbolic lambda x plus v4 into sine hyperbolic lambda x, that will be equal to 0. So that maybe that will become my first equation. Okay. Now at x equal to 0, what will happen? v1 into cos 0 plus v2 into sine 0 plus v3 into cos hyperbolic 0 plus v4 into sine hyperbolic 0, that will be continuous. This is 0, this is 0, so you will have v1 plus v3 equal to 0, so v3 equal to minus v1. Now that gives you some reduced order. Yes. So if you do with the sine and cosine, you can get it in the reduced forms. But that reduced form is good once you are solving by hand, not good once you try to make the programs. Because in the programs, you cannot actually just reduce it. You never know that whether you will get this type of boundary condition or not. Like for example, if this is for the yield, you will not, your life is not that simple. Again, it will get complicated because there will be cos lambda yield, and you cannot say that cos lambda yield equal to 0. No. So you cannot able to reduce. So these are happening for few cases. Okay, that expressing the sine and cos will gives you some sort of reduction, and that will makes your life quite easy. Because if you do this, this will come like that, and then next one will be v2 equal to v4. So now you can see that your from the fourth term, now you are left with two term only, either v1 v2 or v3 v4, whatever. So now your rest of the equations you can just solve only for the two terms. So maybe in the third equation you can get one, expressing one with another, and then you just substitute back full thing to the last equation and solve it. Still the pain will remain, more or less similar of solving that, but in the more reduced form. Reduced form. So that's the main logic that, or main reason that why this method is not get popularized that much. These are mostly like we researchers are using it for like several other very sophisticated applications, you can say. We can use that, but for the real life general normal problems, we generally do not use that.